As we look at section 7.4, we start solving trigonometric equations. Now these are going to bring into play a lot of what we've done so far this semester, looking at not just the trigonometric identities that we've seen here, but really a deeper understanding of what these trig functions do in terms of both triangles and the unit circle. Because I can give you even a straightforward equation, like tangent of theta equals 2, and just solving that requires a little bit of doing. And there's the immediate solution we can think of to take the inverse function. So we get tan inverse of 2. So we get theta. Now tan inverse of 2 doesn't have a nice result, but you get about 1.12 if you plug it into a calculator. That is, of course, in radians. But the problem is the domain of the tangent function, negative pi over 2 to pi over 2. That comes from the definition of the inverse tangent, because if we were to actually graph it out at pi over 2 and at negative pi over 2, the tangent has vertical asymptotes there. So we restricted ourselves to this. But the tangent function, if you remember what its graph looks like, has this sort of behavior. Every pi units, it's got periodicity. So I need to represent this in a different way. And this is the way we'll do it, plus k pi. Now k is an arbitrary integer. It could be 0, in which case we just get 1.12. It could be positive 1, positive 2, negative 1, negative 2, which would move me either in this direction if it's positive, in this direction if it's negative. But for any integer k, this number will make this equation true. And that's what it means to solve an equation. It's to find the values that go in for the variables that make the statement true. Anything of this form where k is any integer will work. So you need to be cautious when you're looking at these things to figure out what the solutions are going to be based on the periodic behavior of the trig function. So do another example. Suppose I had 2 sine theta minus 1 equals 0. Now you can start out adding 1, dividing by 2, your usual algebra techniques, to get sine theta equals a half. Well, we have to ask ourselves, when is the sine equal to 1/2? Now pi over 6 should come to mind immediately from the chart that we constructed so many times earlier in the course. But is that the only possibility? Now the sine, if you go back to our good old friend the unit circle, pi over 6, looking at something like that, and the sine is 1/2. The sine is the y-coordinate. So when is the y-coordinate positive 1/2? Not just at pi over 6, but over here, reference angle of 5 pi over 6. So there's two options right off the bat. The other thing, though, is the sine function is periodic, right? Every time you take one lap around the circle, you get back where you started. Well, what's the distance to travel one lap around the circle? 2 pi. So 2, 4, 6, 8 pi, negative 2, negative 4, negative 6, negative 8 pi. Those will all work. So again, for an arbitrary integer k, we need to add some multiple of k pi. But I can't just add pi. If I started here and just added pi, I'd get over here. That doesn't have a y-coordinate of positive 1/2, so that doesn't work. So I need to always make sure I go around by 2 pi. So I'm going to have to add 2k pi. Again, k is an arbitrary integer, but you'll notice what I added here is based on the period of the sine function. What I added here is based on the period of the tangent function. We can expect the same result to happen over and over again. Let's do another one with a tangent in it. What if I had Tangent squared of theta minus 3 is 0. Well, adding 3 and taking roots, I come up with tangent theta plus or minus root 3. Now I don't know what quadrant theta lives in, so I do need to keep track of both the plus and the minus. I'm going to start out by finding solutions between negative pi over 2 and pi over 2, and then I can add k pi to address the periodicity of the tangent. Again, you go back to our chart that we made earlier, and we see that theta could equal pi over 3, or theta could equal negative pi over 3. But because of periodicity, we'll have to add k pi to account for trips around the circle. So these are some straightforward ones where you can isolate the trig function using a little bit of basic algebra. Hopefully, we're comfortable enough with the charts that we made earlier to look what's the domain of the function and sort these things out. Or, like we saw back here, if we need to use an inverse function, we can do it. But some of them don't look quite so straightforward. Suppose I had 5 sine theta cosine theta plus 4 cosine theta is equal to 0. For something like this, my standard add, subtract, multiply, and divide is not going to work very well. But there's a cosine in both of them. Remember, this is an operator. Cosine takes in theta. This whole thing is treated like one object, and so I can factor it out. I'm left with cosine of theta times 5 sine of theta plus 4 is equal to 0. Well, that's great. If I have a product and it equals 0, that's only going to be true if one or both is equal to 0. So I can treat these things separately. So from the cosine, I'm really just looking to solve for when is cosine of theta equal to 0. Well, when is the cosine 0? Cosine is 0 at pi over 2 and 3 pi over 2. Where else? 5 pi over 2, negative pi over 2. Turns out I don't really even need this one. Plus k pi. Now in this case it looks a little strange because the period of the cosine is 2 pi and I just added k pi. If it helps clarify it, we could go back to that. If I want to add 2k pi, I can get 3 pi over 2. The reason we got these and we got the screwy part was it was in this first 2 pi of the domain of the cosine, there's actually 2 different points where it's equal to 0, and they happen to be exactly pi units apart. So we had that part. The other one, 5 sine of theta plus 4 equals 0, which happens when sine of theta is negative 4/5. Negative 4/5, unfortunately, does not have a nice representation, so we're probably going to have to go ahead and use an inverse trig function here. And we end up with this being about negative 0.93. So, what do I need to add to that? Well, definitely a 2k pi, but again, I need to think about the unit circle. Scroll over here to the side for a second. If I'm at negative 0.93, probably down here somewhere, so I should have something corresponding on the other side. How much am I going to need to add to that? Well, I know that the distance from here to here is 0.93, so the distance from here to here is 0.93. So if I start at the standard position and lap all the way around, that should be pi plus 0.93. So for my second part, pi plus 0.93 and plus 2k pi from the period of the sine. So there was two basic things that I did here. We either were able to break it down into something where it was a value we recognized from our table, and that told us what the angle was. It broke down into something we didn't recognize, and we had to approximate using an inverse trigonometric function. So, in the next section, we'll finish out Chapter 7, and we'll move to some more complicated trig equations.